So we're going to start Chapter 6, which is going to be dealing with area and volume between curves. So for Section 6.1, we're going to talk about the area between two curves. So we're looking at the area between two functions, and we're going to call these two functions f of x and g of x. So suppose that you have two continuous functions on some closed interval, and suppose that one function, f of x, is greater than or equal to g of x between your closed interval. This means that the curve that y equals f of x lies above. Again, since f of x is greater than g of x, that means when you're looking at the graphs, that means that f of x is above the curve y equals g of x, and the two can touch but not cross. To find the area bounded by y equals f of x below and by y equals g of x on the sides by the lines x equals a and x equals b. So here's my closed interval a to b. What I'm trying to do, again, here's my graph of f of x. Notice f of x is greater than g of x because it's above g of x. I want to calculate the area between these two particular curves. So again, to calculate the area between two curves in a closed interval, then what you can do is you can integrate from a to b, and you can subtract f of x minus g of x dx. And again, the way you can remember this is top minus bottom. On these bounds, again, when you're doing the antiderivative with respect to x, a and b are the x values. So to find your limits of integration, again, because a lot of times, sometimes you may have to find a and b on your own, what you want to do is you're going to want to sketch the region. You always want to do a sketch when you're calculating the area and draw a vertical line segment through the region at some arbitrary point on the x-axis connecting the top and the bound of the boundaries. So what I mean by this, to help you figure out top minus bottom, take your pencil on your curve of f of x after you do your sketch and draw a vertical line segment. That way you can clearly see which function's on the top and which one is on the bottom. The y-coordinate at the top of the endpoint line segment sketched in step 1 will be f of x. The bottom one will be g of x. And the length of the line segment will be f of x minus g of x. This is your integrand. Again, this is what's going to go in your integral. To determine your limits of integration, imagine moving your line segment left and right. The leftmost position with the line segment intersects the region x equals a, and the rightmost will be x equals b. So x equals a is your lower bound, x equals b is your upper bound. So again, when you look at your line segment furthest to the right, we move it furthest to the left, that'll tell you your upper bound. So right here would be your upper bound, this is your lower bound. Sometimes they're line segments, sometimes they're going to be points of intersection. So let's take a look at this example here. So sketch the region enclosed by the curves and then find its area. So notice I have two line segments. They're giving me two vertical lines at x equals -1 and x equals 2. Again, I want to sketch the line y equals x. So only between this interval -1 to 2. So again, this is going to be -1 to 2. There's my line y equals x. Again, x squared plus 1. So here's it's a parabola. So again, I know that this is going to look something like this. So here's my line segment x equals 1. Here's my line segment x equals 2. What I'm trying to do is calculate the area between these two curves. So remember, y equals x was the line, y equals x squared plus 1 is my parabola. So again, remember, to figure out the area, it's always going to be top minus bottom. So if I call f of x my parabola x squared plus 1, I'm going to call my line segment y equals x g of x. So you can see that the function on the top is your x squared plus 1. So to calculate this area, it's going to be f of x minus g of x. And you can see this region is bounded between your two vertical lines x equals -1, and x equals 2. So then to calculate this area, it's going to be from -1 to 2, f of x minus g of x dx. Which again, when I plug in my functions, f of x is x squared plus 1 minus x dx. Excuse me, this upper bound should be a 2, -1 to 2. So now when I integrate, that's going to give me x to the third over 3 plus x minus x squared over 2. And I'm going to evaluate this from -1 to 2. So when I plug in my upper bound, that's going to give me an 8/3 plus 2 minus 4/2. Minus, plug in my lower bound, that's going to be a -1/3 minus 1 minus 1/2. So this is going to give me 8/3. And again, this is going to give me a minus. This is going to be -4/3 minus 1/2. So that's going to give me -8/6 minus 3/6, which is -11/6, which will give me a positive 11/6. So that I can rewrite this as 16/6 plus 11/6, which is 27/6, or when I simplify it, 9/2. Again, though, if it's a free response question, you can go ahead and leave it alone just like that. Like I said, it is possible that the upper and lower boundaries may intersect at one or both endpoints. In this case, the sides of the region will be points instead of vertical line segments. When that occurs, to determine your points of intersection, you have to set the two functions equal to each other and solve for x. This will give you the limits of integration. So again, you may have to find points of integration. So for example, find the area between the curves of 2 minus x squared and g of x equals x. So again, we've got the graph y equals x, and then 2 minus x squared. So this is a reflected parabola with a vertical shift going up 2. So we're trying to calculate the area between those two curves. So the issue is, you can see we do not have vertical line segments. We're going to have points of intersection. So the first step is going to be, we have to find the points of intersection so I know what my bounds are going to be. So I'm going to take these two equations and set them equal to each other. So 0 is going to be equal to, I'm going to move everything to the right-hand side, x squared plus x minus 2. When I factor this factors into x plus 2 times x minus 1. So x is equal to -2 and 1. So I know that this point of intersection is going to be when x is equal to -2 something. This point of intersection will be 1 something. So now I can calculate my area. Again, remember the area is top minus bottom. So again, if you can see from your graph that you drew, the function on the top is the parabola, which is your 2 minus x squared. The function on the bottom is y equals x. So to calculate this area, it's going to be my lower bound of -2 to 1. Again, the function on the top is my f of x, which is 2 minus x squared, minus the function on the bottom, dx. So when I integrate, that's going to give me a 2x minus x to the third over 3 minus an x squared over 2. And again, I'm going to evaluate this from -2 to 1. So I plug in 1, that's going to give me a 2 minus 1/3 minus 1/2. Minus, plug in my lower bound, which will give me a -4. This is going to give me, when I cube -2, that's a -8, but that becomes a plus 8/3. Minus 2 squared is 4, 4 divided by 2 is 2. And again, if it's a free response question, I can leave it like this. Or if I was to simplify it all the way out, it would equal 9/2. So that's how you can do area problems involving two curves by hand. So let's take a look at this problem here. Using your calculator, find the area of region R and region S given that f of x is equal to sine of pi x, g of x is equal to 4 negative x. So they labeled, here's your f of x. And I always like to use two different colors here. There's my f of x, which I've highlighted in pink. And then g of x is in blue. So now, even though this is a calculator question, the first thing you're going to have to do is you've got to find these points of intersection where those two regions are intersecting. So what I want to do is I'm going to graph this on my calculator. So I'll go under my y equals, and I'm going to load f of x under y1. I always like to show or know where I've put each function. So I'm going to load f of x under y1. So I have 1/4 plus sine pi x. Under y2, I've got the 4 raised to the negative x. And you can see how we're only looking at this region in the first quadrant. So what I'm going to do is I'm going to readjust my window. I'm going to go my window, do an x min of 0, x max to 10. I'm going to shrink down my y min a little bit and go from 0 to 5. So you can see this is the region I'm actually looking at. So I'm going to shrink my x mins down a little bit so I can look at the graph a little bit better. I want to take this down to a 5, and this to maybe a 3. I could probably make it a little smaller just to help me. See what that does. That's a little better. So on my calculator, this is my region R, this is my region S. So to find the points of intersection, I'll go to our second trace, intersect. Doesn't matter which one I find first. This is going to be 1 and 0.25. Second trace, intersect, find my other one. So this point's going to be 0.178 and 0.781. I just get in the habit of writing both the x and the y because later on in this chapter you may need to have both the x and the y. So now let's talk about finding the area of region R. So notice the function on the top is your g of x. So